Let's investigate the Cauchy criterion for convergence in probability. So a sequence of random variables, x1, x2, x3, and so on, converges in probability to random variable x if the limit as n goes to infinity of the probability that the absolute difference between xn and x, so that's the absolute value of xn minus x, exceeding a given positive number epsilon, that this probability should go to 0 as n goes to infinity. And this must be true for every strictly positive epsilon. Now, one problem with this definition is that to check it, we need x, we need the limit random variable, which sometimes it can be guessed, sometimes it is very hard or even impossible to guess what x should be. So we have the Cauchy criterion, which tells us that we do not need x to investigate convergence. We can just work with the sequence itself. And so the alternative definition is that we will have the difference between xn and xm, then take the absolute value, and then we will investigate the probability of this distance exceeding any positive epsilon. We have convergence in probability if and only if this tends to 0 when we take the limit of n and m going to infinity. So let's prove this. Now, we have two parts. Given that we have limit n tends to infinity of this probability is equal to 0. Now, the goal is to show that limit n tends to infinity, m tends to infinity, this probability is also 0. And this is true for every positive epsilon. Now, let's start with this one, with this limit. Okay. And what we will do is that in this absolute value, we will insert plus x and minus x. So here we have probability. Now we have xn, and then we have minus x plus x minus xn. So this probability is upper bounded by the following sum. So the probability that absolute value of xn minus x greater than epsilon over 2 plus probability of absolute value xm minus x greater than epsilon over 2. So here this is xn minus x, here it is, and this is x minus xm, here it is xm minus x, we don't care, we have an absolute value. So what is this inequality? The general case is that we have probability of absolute value of a plus b being greater than epsilon. This is upper bounded by the probability of absolute value of a greater than epsilon over 2 plus the probability that the absolute value of b is greater than epsilon over 2. So here xn minus x is like a and x minus xm is like b. Why is this true? Well, the event that absolute value of a plus b is above epsilon implies that absolute value of a plus the absolute value of b is greater than epsilon. And why is this the case? Because of the triangle inequality, because the absolute value of a plus the absolute value of b is greater than or equal to the absolute value of a plus b. So this is the triangle inequality. This means that the probability that the absolute value of a plus b being greater than epsilon, this is upper bounded by this probability. Now, if A is less than or equal to epsilon over 2, and B is less than or equal to epsilon over 2, then their sum is less than or equal to epsilon. Now, what is the contrapositive? Absolute value of A plus the absolute value of B greater than epsilon. So this is the negation of this proposition here. This implies that either absolute A exceeds epsilon over 2 or absolute B exceeds epsilon over 2. So this means that this upper bound that we have here can be also upper bounded by the probability of A, absolute value of A greater than epsilon over 2, union absolute value of B greater than epsilon over 2. Finally, we can apply the union bound. So this probability of the union is upper bounded by the probability of absolute A greater than epsilon over 2 plus, so the union bound is to upper bound the probability of the union by the sum of the probabilities. And this is exactly what we applied here. Now, what is given is that limit n tends to infinity, the probability of absolute value of x n minus x greater than epsilon is equal to 0. So, of course, epsilon here again, this is, for every epsilon that is strictly positive. So, in other words, if we take the limit, this guy will go to 0 and this guy will go to 0. And this, this probability, when we take the limits, is upper bounded by 0. So this limit itself, of course, because it is greater than or equal to 0, this limit itself will be 0. And so this is one direction. The other direction is that now this is the statement that we have. Limit n tends to infinity, m tends to infinity of this probability xn minus xm greater than epsilon. This is equal to 0 for every epsilon that is greater than 0. Now the goal is to have limit n tends to infinity of probability xn minus x. So here from this statement, we go to the other statement saying that there must exist a random variable big X such that the probability of the absolute difference xn minus x being greater than epsilon, that this goes to 0 as n goes to infinity. Now, what should we do? One consequence of the given limit is the following. So if this limit is true, and it is true as given, then for every positive integer k, there exists some v of k such that for every n and m greater than or equal to v of k, we have the probability that absolute value of xn minus xm being greater than 2 to the minus k. This probability is upper bounded by 2 to the minus k. So this follows from the given limit statement, because this statement is true for any epsilon that is strictly positive. So I can use an epsilon that is in the form of integer. And since the limit is equal to 0, it means that this probability can be made arbitrarily small by choosing n and m that are large enough. Okay, so this is a consequence of the given. Now, suppose that we have the following positive integers. N1 is equal to V1. Then we take N2 to be the maximum of V2 and n1 plus 1, and then n3 to be the maximum of v3 and then n2 plus 1. So you can see the pattern that n sub k is the maximum of vk and then nk minus 1 plus 1. So this is an increasing sequence of integers. Now take n2. n2 is greater than n1, and n1 is set to v1. So this means that both of them, n1 and n2, are greater than or equal to v of 1. So if we go to this statement here, this means that the probability of the absolute value of x n1 minus x n2 greater than 2 to the minus 1 must be less than 2 to the minus 1. So this is the case in which k is equal to 1. Since these two integers are greater than v of 1 by design, then this probability is true. Now, n3 is greater than n2, and n2 is greater than or equal to v of 2. So the two guys, n2 and n3, both are greater than v2. So this implies that the probability of xn2 minus xn3 being greater than greater than 2 to the minus 2, this is upper bounded by 2 to the minus 2. So this is an application of this statement for k equal 2, and so on and so forth. Okay, so we can obtain or construct a subsequence x and k, where k is a positive integer, satisfying that the probability of x and k minus x and k plus 1 greater than 2 to the minus k, this probability is upper bounded by 2 to the minus k. So from our original sequence of random variables, we can obtain a subsequence, and this subsequence basically satisfies this probability for every positive integer k. Now let's examine the probability of union k greater than or equal to m, x n k minus x n k plus 1 minus 0 greater than 2 to the minus k. And specifically, we will be interested in the limit of this probability as m goes to infinity. So what we are doing is that we are investigate the almost sure convergence of xn minus k minus xn k plus 1 to 0. Okay, so this is the test of almost sure convergence, or this is one of those tests. We will examine the probability of this union. And of course, we can upper bound using the union bound. So probability of union is less than or equal to the sum of probabilities. And now we can apply this inequality here, that those probabilities by design, each probability with k here is upper bounded by 2 to the minus k. So this is a geometric series. So this is minus m plus 1. And this goes to 0 as m goes to infinity. So here the answer to this is yes. We have this almost sure convergence. So the difference converges almost surely to 0. Okay. So basically, the subsequence x and k is actually a Cauchy subsequence, okay, or a Cauchy sequence. We can see it that, like if we give more details, that this probability state, this convergence statement is true. So we have by continuity of probability. So now we have 0 is equal to the limit as m goes to infinity of this probability that we have just investigated. This is equal to 0 by the continuity of probability, which we can apply here. This is the probability that intersection m, so m is an integer that is greater than or equal to 1. So the probability of this event is equal to 0. So what about the complement? So now we have the probability of union m greater than or equal to 1 intersection k greater than or equal to m of x and k minus x and k plus 1 less than or equal to 2 to the minus k, that this probability is 1. Okay, because this event is the complement of that event. Okay, so how to read this? We would say that there exists a value of small m. There exists a value for small m. Okay, let's say that this value is m tilde. Okay, so there exists m tilde, which is an integer greater than or equal to 1, such that for this m tilde, we have this intersection. For every k that is greater than or equal to this m tilde, what do we have? We have that this inequality, x and k minus x and k plus 1, after taking the absolute value, is less than or equal to 2 minus k with probability 1, or we can say almost surely. So for this subsequence x and k, there is an index m tilde, and for every k greater than or equal to m tilde, then this difference is less than or equal to 2 to the minus k. This is with probability 1. Okay. Now, to show that actually the subsequence is a Cauchy sequence, okay, let's basically, now fix some epsilon that is strictly positive, and set m bar. Let's take it to be greater than, initially I will take it to be greater than m tilde. So greater than m tilde, so so that we have this inequality satisfied. Take r greater than s greater than or equal to m bar. Let's investigate the absolute value of the difference x and r minus x and s. Let's try to express this difference here as a telescopic sum. So this is summation v from s to r minus 1, x and v plus 1 minus x and v. Okay. Then apply the triangle inequality. And so this will be summation v equal s r minus 1. And then we can take the magnitude or absolute value of this. The terms in this sum are non-negative, and so we can upper bound this sum by a sum just going to infinity. And then we can apply our inequality here. and this is a geometric series, and so the result is 2 to the minus s plus 1, and now s is greater than or equal to m bar, so this is less than or equal to minus m bar plus 1. And the idea is, can we make this less than any arbitrary positive epsilon? Yes, of course. Okay. For example, if you choose m bar to be strictly greater than the ceiling of minus log to the base 2 epsilon over 2, if this is the case, then m bar is greater than minus log to the base 2 of epsilon over 2. So 2 to the m bar is greater than 2 over epsilon, and this means that 2 to the power 1 minus m bar is indeed less than epsilon that we have here. Okay, so this means that, if we set m bar to be greater than the maximum of m tilde, we need m bar to exceed m tilde so that we can go from here to there. Okay. So we will have m bar greater than the maximum of m tilde and the ceiling of minus log to the base 2 epsilon over 2. Then we are able to make this absolute value less than any arbitrary positive number. Okay, and this is exactly the meaning of a Cauchy sequence. So the conclusion is that x and k as a sequence, this is a Cauchy sequence with probability 1, and due to the completeness of the set of real numbers, then x and k converges. Okay, so we have xn of k converges almost surely to random variable x. So if this is true, there must exist a random variable x such that x and k converges almost surely or with probability 1 to x. Now, this implies that x and k converges in probability to x. As a reminder, consider a sequence Zn converging to Z almost surely. Then the probability of intersection n greater than or equal to m, Zn minus Z less than epsilon. This is the probability of the intersection, and it is upper bounded by the probability of absolute value Zj minus Z less than epsilon. And here we can use j, that is any number that is greater than or equal to m. So what we'll do is that we'll take the infimum of both sides with respect to j. So the probability of the intersection is less than or equal to infimum j greater than or equal to m, the probability of absolute j zj minus z being less than epsilon. Now take limit of both sides as m goes to infinity. So in this case, left-hand side converges to 1. Why? Because Zn converges almost surely to Z. So this is the definition, or one of the definitions, of almost sure convergence. And so we have that limit infimum m tends to infinity, probability absolute Zm minus Z less than epsilon, that this is equal to 1. And this means that the limit supremum is also equal to 1. And so we have that limit m tends to infinity, the probability of Zm minus Z being less than epsilon is 1. And so the sequence, if it converges almost surely, then it also converges in probability. So back to our case, if the subsequence, so we established that the subsequence is a Cauchy sequence, so it converges almost surely to some random variable x. So we also have convergence in probability. Our final step is take limit n tends to infinity of this probability. Okay, remember that it is this limit that we want to show is equal to 0. What we'll do is that we will assume that there is another guy, and we'll take the limit also as k tends to infinity. Okay, of course, these two limits are the same because here this probability, it does not depend in any way on this new guy k. Then we will modify, it's an equality, we'll have probability, we will add x and k and subtract x and k. Then I will apply the same inequality that we established at the beginning, which is this inequality here. So this is less than or equal to n tends to infinity, k tends to infinity, xn minus xnk greater than epsilon over 2 plus limit. Of course, here I'm using the linearity of limits, probability of the absolute value of x and k minus x greater than epsilon over 2. Now, because we have this convergence statement that x and k converges to x in probability, so this limit is 0. And this is also equal to 0 as desired because of our given limit statement that basically this probability is equal to 0 for every, here we used n and m. So because this is true, then this limit here is also equal to 0. And so this limit will be equal to 0.